Welcome back to Physics with Han. Today we're going to be looking at refraction. I've got an optical fibre here and we're going to be looking at how that works at the end. Now here you can see a red laser light and a rectangular perspex block. You can see here that the red laser light is just passing straight through the perspex block with no deviation in direction. As I change the angle that the laser light is incident, you can see that the light starts to bend as it passes through the perspex block, and then it bends back when it exits the block. And this is refraction. So all waves can refract, and this happens when waves pass from one medium to another. These mediums need to have different refractive indexes in order for the light to actually change direction. Some examples of this, we could have waves travelling into oil, into glass, or maybe into water. So what is the refractive index then? Refractive index is a property of a material and it's given the symbol N. In order to figure out N, you can use the ratio of the speed of light in a vacuum over the speed of light in that given material. So if we're looking at glass, if we want to find the refractive index of glass, we're going to divide the speed of light in a vacuum, which is 3 times 10 to the 8 meters per second, by the speed of light in glass. The refractive index of air we say to be 1 because it's the speed of light in air is very similar to that in a vacuum. Okay, so let's analyze this image here, which you just saw in the previous clip. So here the dotted lines are representing the normal lines, which are always at 90 degrees to the boundary. Theta 1 is my angle of incidence and theta 2 is the angle of refraction. And then I've also labelled 2 more angles, theta 3 and theta 4, to show the angles of incidence and refraction at the other end, at the other boundary. So here theta 1 is bigger than theta 2, and this tells us that the refractive index of the perspex is bigger than the refractive index of the air because the laser light has bent towards the normal. An equation that will come up on your data sheet is Snell's law. N1 sine theta 1 equals N2 sine theta 2. So you need to make sure that you're consistent with measuring your angles in degrees. And this ratio will enable us to find the refractive index of a substance, or maybe the angle of incidence or the angle of refraction. Okay, so what actually happens when waves refract? So we've been talking about light, so we'll continue to just talk about light here. When light enters a medium with a higher refractive index, it will slow down. The frequency of this light, though, will stay the same, which is important to remember. Something that does change, though, is the wavelength. And if you remember the equation, wave speed is frequency times wavelength, that will hopefully make a bit more sense. To help you remember this, think of a marching army. They have to march in step to a certain frequency. If they're marching from concrete and then all of a sudden they move into onto a ground such as like sand, mud, or maybe through water, their stride length is going to decrease, but their frequency will still stay the same. The relative refractive index between 2 materials is the ratio of the speed of light in material 1 to the speed of light in material 2. This equation can be combined with the one that we looked at before, saying that the refractive index is equal to the speed of light in a vacuum over the speed of light in a certain material. And that gives us the relative refractive index in terms of the ratio of the refractive index of material 2 over the refractive index of material 1. Let's have a look at an example. Here we have lights entering a boundary between material 1 and material 2. This diagram is being given to us, and we can clearly see that the light ray is bending towards the normal in material 2. So we would expect that material 2 would have a higher refractive index because of this. We're given the refractive index of material 1 and the angle of incidence and angle of refraction. So the equation we're going to use here is Snell's law. N1 sine theta 1 equals N2 sine theta 2. We need to rearrange this equation because we are trying to find N2. So to get N2 by itself, we need to divide both sides by sine theta 2 to give us this rearranged version of the equation. Now we just need to substitute our numbers in. So N1 is 1.1, theta 1 is 39.5. And theta 2 is 29 degrees. So the refractive index of material 2 comes out at 1.44. If you look at the question though, the smallest number of significant figures we're given is 2. So we should also give our answer to 2 significant figures as well. So the answer is 1.4. All right, back to our laser beam. This time I've got a semicircular perspex block. At this point here, the light again passes straight through because it's entering the boundary along the normal, so it will not change direction. As I increase the angle of incidence, you can see that now we're getting refraction on the boundary between the air and the perspex block, and then back out the other side from perspex block into air. However, as I keep increasing the angle of incidence, you can see that some of the light starts to actually reflect at that boundary between the perspex block and the air. And in fact, now all of the light is completely reflecting. And this is called total internal reflection. And like with normal reflection, for example, off a mirror, theta 1 is going to be equal to theta 2 because that's the law of reflection. The angle of incidence is equal to the angle of reflection. Okay, so like I said, this is called total internal reflection, which means that all of the laser light is reflected and it stays in the medium that it was initially traveling, which was the perspex block, rather than leaving the block and heading back into air. So there are some conditions for total internal reflection to happen, and these are that theta 1 must be bigger than an angle called the critical angle. How do we find the critical angle? You can do this practically by just moving the angle of incidence so that we get all of the light reflected. But we can also use this equation. Sine of the critical angle equals N1 over N2. The conditions for this are that N1, the refractive index of material 1, must be bigger than the refractive index of material 2. So for example, it will work if we're going from glass into air. A relationship we can use is the refractive index in material 1 is equal to 1 over sine theta c, and that can be derived by the above equation. This is another demonstration of total internal reflection. You can see that at each boundary, the light is being reflected and staying in this perspex core. This is an example of how fiber optic cables work. And going back to the video that I showed you at the start, you can see that I've got a bundle of fiber optic cables. There's a light source right at the start, which is totally internally reflected all the way through these fibers until the light reaches the end where it is refracted out.